In an age where the intricacies of technology can both empower and intimidate, distributed computing stands as a beacon of progressive complexity and potential. This domain, which orchestrates harmony among a myriad of interconnected computers, is not just a technological endeavor, but a revolutionary approach that reshapes how we perceive and interact with data across the globe. Distributed computing at its core is about efficiency and scale. It enables computers to work together over a network to achieve common goals, tackling tasks that would be impossible for a single machine due to resource constraints or computational demands. This foundational strategy is crucial in an era dominated by big data and complex real-time processing requirements. Distributed systems are not a new concept, but their applications have become increasingly vital as the Internet has evolved. From the early days of the ARPANET to today's sophisticated cloud infrastructures, distributed computing has grown both in complexity and importance. This guide aims to demystify the foundational elements, advantages, and challenges of distributed computing, making it accessible to Internet programmers and technology enthusiasts alike. Understanding a distributed system begins with two primary components: nodes and network links. Nodes, or computers within the network, each operate with their own memory and processing power. Network links, on the other hand, are the communication channels that connect these nodes, allowing them to function as a cohesive unit. Nodes vary widely in their capabilities and roles within a system, ranging from powerful servers to simple sensors. The diversity among nodes reflects the system's ability to handle varied tasks and data loads effectively. Network links can be wired or wireless and utilize different protocols to facilitate efficient data transfer between nodes. This structure supports the system's ability to scale and adapt to different computational and storage needs. One of the defining features of distributed systems is concurrency. This allows multiple processes to run simultaneously across different nodes, significantly speeding up computation and enhancing system responsiveness. Another unique aspect is the lack of a global clock. Each node operates on its own clock, and time synchronization across the system is a major technical challenge. This decentralization of time management is crucial for the independence and flexibility of each node. Independent failures are another critical characteristic. In a distributed system, if one node fails, it does not necessarily mean the entire system fails. This resilience is pivotal in maintaining system integrity and continuous operation despite individual mishaps. Distributed computing is driven by several goals, chief among them being resource sharing. By pooling resources, whether they are computing power, storage, or data, systems can accomplish more than what individual nodes could achieve alone. Scalability is another fundamental goal. As demand increases, distributed systems can scale horizontally by adding more nodes or vertically by adding more power to existing nodes, thus maintaining performance without a costly overhaul. Fault tolerance and transparency also play crucial roles. Systems are designed to handle failures gracefully and to hide the complexities of the operations from the end user, providing a seamless experience. The advantages of distributed computing are substantial. Reliability is enhanced as the risk of total system failure is reduced. If one node fails, others can take over its tasks. Performance benefits are also significant, as tasks can be distributed among nodes, allowing for faster processing and less strain on individual components. Scalability, a key advantage, allows a system to expand and contract its resource pool as needed without significant downtime or performance degradation. This flexibility is crucial for businesses that experience varying workloads. Despite its many benefits, distributed computing brings substantial challenges. The complexity of designing and managing a distributed system is significantly higher than that of a single-node system. Security is also a major concern, as the interconnected nature of the systems increases vulnerability to attacks. Ensuring data consistency across multiple nodes can be difficult, particularly in real-time applications. Network issues, such as latency and bandwidth limitations, also pose ongoing challenges. The architecture of a distributed system can significantly impact its efficiency and capability. The client-server model is widespread, where multiple client nodes request and receive services from centralized server nodes. This model simplifies some aspects of network design but can create bottlenecks. In a peer-to-peer P2P network, nodes act as both clients and servers, creating a more resilient and scalable system, but increasing complexity. The microservices architecture breaks applications into smaller independent services that communicate over a network, enhancing flexibility and scalability. Several key technologies enable distributed computing. Communication protocols like HTTP and TCP/IP are foundational for node interaction. Middleware such as Apache Kafka and RabbitMQ facilitates communication and data management across disparate systems. Distributed databases like Cassandra or MongoDB provide the backbone for data storage and retrieval across the network. Moreover, cloud platforms like AWS and Google Cloud offer scalable resources and services that support the deployment and management of distributed applications. Distributed computing is a dynamic and essential field in modern technology, offering significant advantages while posing unique challenges. As we look to the future, advancements in network technology, artificial intelligence, and quantum computing will likely drive further innovations in distributed systems. This guide provides a foundational understanding for Internet programmers and enthusiasts looking to delve into distributed computing. As technology evolves, so too will the strategies and solutions in this fascinating and crucial domain.